Hello, everybody. As Tom said, my name is Javier Calderon Sanchez from Universidad Politécnica de Madrid in Spain. And I am going to present today collaboration work that we are doing with the Universidad de Costa Rica, in particular with Juan Gabriel Monge Gaper and Alberto Serrano Pacheco. And this collaboration is about multi-phase simulations of nonlinear fluids with SPH. It's been almost 2 years working on this topic, and I have to admit that our background here at Universidad Politécnica de Madrid was not in particular on non-Newtonian or nonlinear fluids, so it's been a real challenge. But now that we are starting to see some interesting results, it's very satisfactory. So what I will be talking today, I will start with the motivation of this work and putting it in context, and then I will explain straightforward what's the SPH model that we are using in order to achieve our aim. And I will finally present some of the test cases that we have been trying along this time. And of course, I will end up with some conclusions and some lines for the future. So you have here an image of what to expect. That is basically, we are not considering a constant viscosity field anymore, but we have to deal with the variable viscosity defined at each of the particles. So the motivation comes from the fact that there are tropical storms happening in Central America, and just as an example, you have this Niña phenomenon that happens not cyclically but every several years, and brings mudslides such as the one that you can see that happened in 2019 in Golfito in Costa Rica. So the fact is that these kind of events are growing, and in particular in Costa Rica, it's damaging some very populated areas. And then authorities are worried about this fact and are putting efforts on trying to mitigate and prevent these kind of events. But it's not only about Central America. It's a fact that mudslides are growing, and these kind of events are a global phenomenon that it's intrinsically linked to climate change. So it's interesting to analyze it from not only for a particular event, but for global events that might happen. And one of the particular aspects of these mudslides is that they mix and they include the linear and nonlinear dynamics, and that's why we go and we started studying the nonlinear dynamics for this problem. So just as an example of what to expect in one of these events, this in particular happened in Switzerland, but you can see what kind of flows, what kind of properties you can expect, and also which are the damages that they might cause to the infrastructure or houses, or even a risk for people, because the fluid advancing has a lot of strength, so and impact. So it's something really impressive and deserves our attention. So after this, the aim that we set is to be able to model the evolution of a two-phase flow that includes both linear and nonlinear fluids. And this includes mud, salt, and other phases of viscoplastic fluids that might or might not have high yielding points. And for that, we are going to use an equivalent viscosity field approach. So this is the SPH model that we are using. It's a weakly compressible formulation, and you have a, I mean, it's a continuity equation with a delta SPH as implemented by, or as introduced by Marrone et al. In 2018 or 2011, sorry. There's also momentum equation, and for that we used a similar approach to the one presented by Furtakas and Rogers or Subeldia previously, also for weakly compressible approaches. And we have also included the shifting in our formulation, and the type of shifting that we have included is same fashion as the latest formulations, and some of these are analyzed in the paper by Julien Michel et al. And we are at the moment using the Peng and Sun formulation, but exploring alternatives, and in particular the one proposed in this paper. For boundary conditions, we are using a boundary integrals technique as introduced by Serkos-Pita in 2015. This is an approach where the truncation that happens at the boundary is modeled by two effects. One is to include the surface integral along the kernel support, that and we include this by modeling the wall as a set of particles that are defined by an area and a normal. And the other effect is that we renormalize with the shepherd, and there is also some work on this that has been done in previous years in order to define it semi-analytically and have accuracy in this term. So I didn't mention, but for the momentum equation, we have now, what we are doing is to model directly the stress tensor. So we can divide it in the pressure term and in a stress shear term. And the main question here is how to model this second term. And for that, the central concept that we use is the effective or an effective viscosity approach. And this is valid both for linear and nonlinear phases, which is interesting because made us possible to make the model as general as possible, which is a desirable thing that we wanted to achieve, because we are going to mix some linear dynamics and nonlinear dynamics. So we can use the same approach for all the phases included. And in particular, we model the stress with an effective or equivalent viscosity, and we have the strain rate tensor defined as usual in the literature. And for this effective viscosity, what we use is a Herschel-Buckley-Papanastasiou model, and the equation is as the one that you can find here, where you have a flow index, which is kind of or similar to viscosity, or behaves as the viscosity in a Newtonian fluid, the consistency index, and the yield stress. This equation allows us to model several kind of nonlinear fluids, depending on how these terms are defined. Then you have one or other behavior, including also the Newtonian behavior. We have to be aware because there is a discontinuity close to yielding point, and for that we just included an expansion term based on a Maclaurin series, as was introduced by Bilota last year. So what we do is we have to be careful, because when a strain tensor, when the modulus of strain tensor is 0, there might we might have numerical issues from this term. So for that, what we do is just to expand it with this series. We can also include Drucker-Prager yield criterion, and this is something that we have, or we are exploring. And this way, basically what we can do is, or we can include it in order to compute local yielding stress and according to these expressions. So we have 3 test cases that we have been working with. In particular, I'm going to talk a bit about the single phase nonlinear 2D dam break that is based on the work done by Li and Zhao in 2018. Then we will move to a multi-phase tilted up 2D dam break, including a linear and a nonlinear phase that is based on experiments done by Busogi last year. And finally, we will introduce what we are currently working with, and that is to extend the formulation to 3D and be able to analyze 3D cases. And these are some of the coefficients and the terms that we are using. So we have a quite a high range of yield stress. We keep on flow index and the consistency index quite stable because I mean, we have been doing some experiments, some numerical experiments to see the influence of varying these, but they are not as big as the yield stress, at least for the applications that we are testing. And we also can change the density. And you see that, for example, for the multi-phase, we have ratios not over 3. So they are quite low density ratios. So these are the results for our nonlinear dam break when compared to the experiments. And as you see, if we compare the fronts at different time steps, what we see is that we find a relatively good match between them, even though we are losing some material just in this area on top of the front. Let's see if videos work. So I'm going to show first, or my aim here is to show you how the behavior changes when just by changing the yield stress term. So I'm just, let me know if you cannot see, but this is a usual dam break as we are used to see it with water, basically. We are using water viscosity, and here you can see the strain rate, the modulus of the strain rate value. And as soon as you include the sum of yield stress, then you can see, that several things happen. On the one hand, you can see that there is a longer time for the front to evolve and reaching the impact. Then you see that now the fluid starts behaving differently, and you have relatively different behavior after this impact. And this effect even grows when you go to high values of yield stress. So I show the strain rate. I'm going to show the shear stress, for example. So what you see is that now the wavefront starts to grow, and you see that the impact at the end reduces, the violence of the impact reduces, and also that especially this part takes longer to move on to its final position. We kept on we kept on increasing the yield stress up to 700 pascals, and that range of values, what you see is that you're starting to you start to see that the front at the point stops moving. So with this, you can see that there are, or the differences in the behavior of the different of the same model with different values only for the yield stress. So once we had good results for our nonlinear dam break model, and the main outcomes that we can extract is that in general, the general shape maintains for longer time, and that we lose the splashing, the rollover, and the formation of waves that we had for example, for the water dam break. We moved on to the multi-phase formulation with this test case, that is this silted up dam break. And what we see when we analyzed the surface profiles for both sand and water is that we have a relatively good match. And if we compare the front evolution, we can again say that at different points, the evolution in time is relatively nice. Again, we can have a look, for example, the pressure field for this case. So you see that the water flows over the mud, and in this case that we have a high yield stress, what you see is that the surface slightly opens at several locations, and moves to the right relatively slow without hitting the other wall. And finally, we are working on some 3D simulations. So we are especially interested in a channel discharge into a silted pool. We don't have a reference yet for a 3D case, but this is somehow similar to the tests that we were doing to Busogi, and we are now playing with the height of the water column to see or to reach speed or a relatively high speed that induced yielding on the mud. So this is what we are basically working on. You see that the water falls, hits the mud, and the mud deforms or once receiving the impact from the water column. So as a conclusion, we have implemented a weakly compressible SPH multi-phase formulation that allows for both Newtonian and non-Newtonian fluids, and is relatively complex, including shifting delta SPH and let's say corrections that are state of the art right now in SPH. We managed to get accurate results for both non-Newtonian and combinations of Newtonian and non-Newtonian fluids for 2D cases, and we are currently working on the 3D model for the interaction of floods and mudslides, and we hope to have results in the near future. And as part of this work, we have been developing a part of the open source tool Aqua GPSPH, which is the one that we have been using to carry out the simulations, and we hope to have a release of this implementation in just a few months. That was all from my side. Thanks for your attention, and now I will be glad to answer your questions.
Thank you, Javier. There are a couple of questions. So first one from Renato Vacondio. So the tau field, so I guess that's the shear stress field, is quite noisy with a lot of spurious oscillations. Can you comment on that and any plans for improving?
Yeah, I mean, yeah, that's true. There is one big improvement that we achieved in the last months that was including shifting, and that it was kind of magic. It improved the results dramatically compared to what we were achieving a few months ago. But yeah, there's still work to do. My feeling, we are still studying this aspect to see if we can improve more the results. And yeah, that's the moment the plans. We are focused on having a relatively stable formulation, and it's sometimes difficult when impacts are occurring too in the simulations, and yeah, I don't know if we can do, or at the moment we are not we don't have any much more ideas on what to do to improve the oscillations or the spurious oscillations on that field.
Okay, so
yeah, okay, sorry.
Yeah, carry on.
No, it's I'm seeing the question that it's using delta SPH should have reduced pressure noise. It's in the same fashion, I mean, or the same style of question. So there's still some kind of pressure noise. Yeah, I mean, we noticed that as I mentioned, this especially when impacts occur. Yeah, the delta SPH is activated, and what I can say is that it reduced the pressure noise compared to what we had, same as shifting, but of course there's still work to do. Okay, so thanks, Aaron. I will have a look at the papers from Feng from last and this year.
Yeah. Yeah, so the question, it's suggestion by Aaron English to look into papers of Feng published in 2021 and 2022 to reduce the noise in the stress field. So for those of you who are not looking at the Q&A window, I think as attendees you do not see all the questions probably. So that's what Javier just commented on. So I'm a bit intrigued by something you said. I think it was just the Newtonian dam break, where you said we are losing a bit of mass compared to the other simulation.
No, I mean, yeah, what I was trying to say is that if you look at the front shape or you look at the shape of the dam break at the front, we are losing some fluid in a part where it was recorded in experiment. So we expect like a thicker front that the one that we are obtaining. Anyway, we are, I mean, there is this is a model, and there is some sensitivity on some of the coefficients that we are using. So this could be a reason trying to model this with only the Herschel-Buckley equation might be limiting us for capturing these details. I'm not sure yet, but we are exploring why this is happening.
Okay. Are there any other questions?